Before we start today's lesson, I want to tell you that these problems in this packet closely follow our textbook type of problems. So you should be able to hopefully work through all these. I do want to call your attention to chapter 7, number 9, which is the next to the last page. It starts off with simplify, and you see sine of 9t in the numerator. It's right up here, number 9. Has everybody found that? Put a big X through that. There was one section we did not cover, or one part of a section, I think it was in 7.2, sum to product and product to sum. We left that out. Remember that section was huge, and we actually covered it over 2 different lessons, so you can cross that out. When you see something, I also want to call your attention to number 7 under chapter 7 review. Number 7 says sine of x equals 1/8. Everybody found that one? You see where it says tangent 2x, number C, tangent 2x? Now we didn't cover specifically but A is sine of 2x, right? And B is cosine of 2x. Now, even though we didn't cover a double angle formula for tangent of 2x, remember, tangent of 2x is just sine of 2x over cosine of 2x. So once you find the answer for A and the answer for B, C is just that ratio, okay? So even you don't have to use a special double angle formula to do part C. So I handed this out early because I know some of you, time management wise, need to, divide up your week so that you can do it in little pieces. I wanted you to have this in case you could get an early start. And I know others of you will probably start doing it on Thursday night. So, I mean, there's a wide range of people's philosophies here. So let's start with section 8.1 today. Again, I want to just point out something really little, but I think you might enjoy seeing this, is up in the top left-hand corner. You see the title of today's section, but you see optional video. The law of sines, should be saying the law of sines, the ambiguous case. And you've heard me mention before that on our Moodle site, with each mom section, there's optional videos that you may watch or may not watch. I don't know if you've ever watched any of them. But the one on the optional video that talks about the ambiguous case is a really nice visual for one of the things we're going to talk about today. So I would encourage you to check that out. Okay. If we have time, I'll also show you a little what's called Geometry Sketchpad. It's a software package that allows you to do a lot of different things. And Ian Winokur put together a nice visual for the ambiguous case as well that I can show you. So we'll see when we get there if we have time. So what do you think the preview exercises we're having you do? Why did I give you these preview exercises? Nobody knows? Huh? Fresh up on algebra, particularly with the idea of proportions, because I think that as a society we're very weak with proportions, at least in the American sort of education system. So also you notice here that in every single one of these problems you see the sine of an angle. Notice we're now back to degrees. So the first thing I'm going to do for today is I'm going to change my calculator mode back to degrees. It's from radians. Phew. Thank God I remembered to do that one now. And then I better change my Wabbit. So if you have a graphing calculator for tonight's homework, you should do exactly, this should be the very first thing you do. All our work today will be in degrees, okay, in terms of finding the measurement of the angles. All right. Yeah, so when we have two equal ratios, which is called a proportion, AD equals BC. You can go from this equation to this equation. And some people know that as cross products are equal. The only problem with this, and why we don't do this a lot like in levels below Math 108, is people confuse this idea when they're multiplying fractions. So if you have A over B times C over D, you don't do the cross products. And sometimes students, when they don't understand arithmetic very well, and then it translates to algebra, they just start mixing stuff up. So this is one of the strategies you can use in today's section. So start us off, big booming voice. Hazel, number 1. Since I don't have it in front of me. Turn it back on. There'll be some geometric properties that come into play today, and some of you, depending on how long it's been since you've had geometry, might need a little review. But this particular triangle we know is a non-right triangle. Does anybody know what we might call this triangle if it's non-right? Scalene, if all the sides are opposite, yeah, and they certainly look, are not the same, yeah. Scalene, another name for isosceles is when you have two sides the same. Obtuse has to do with the measurement of an angle, so let's put these down. Obtuse, acute, so these are measurements of angles, and that's a little sign for angle. Yeah, you probably may not be familiar with these words. They're called oblique. Sounds like something that I would hurt in my personal trainer exercises, you know. Oblique triangles. Those are non-right triangles. Okay. So in this particular case, this drawing of an oblique triangle, I don't know anything about the measurements of the sides, so I don't know if I can call it an isosceles triangle, which Jackson suggested, but I do know something about at least the way I've drawn this, about these angles. Can anybody tell me what you think about those angles? I shouldn't put any marks in here. Take those out. And what do you think about those, the measurement of those angles? What do you know about them? You know that if you add angle A plus angle B plus angle C, they all add up to 180 degrees, okay? And in this particular case, the way this is drawn, you know that they're all acute. Does anybody remember what acute angles are? Less than 90. And so they would be less than 90 and greater than 0. What about obtuse? It's greater than 90, yeah. The angle's greater than 90 degrees. Okay, so you could have another oblique triangle, maybe that looks something like this. So this angle here would be more than 90 degrees. Okay, so these are the types of triangles we're going to be talking about today. This is some of the language you might hear. I'm trying to think about one. Oh yeah, here's another little geometry fact. You have a straight angle. What's the measurement of that angle? That's 180. If you cut that angle and you call this theta, this one is 180 degrees minus theta. Those are called supplemental angles, when you have two angles that add up to 180. Okay, so let's start today's material. So very unusual for me, instead of starting you off with proving a situation, knowing that time is a consideration these days, at least from what I've seen up here, I'm just giving you the law of sines and cosines. And then I told you the proof of both of these is in your textbook. And I know some of you are reading the textbook. So let's start with some usage of these laws today. So we have a store that has a triangular sign. What I think about is the Citgo sign above Fenway Park there that you always see is a triangular sign, isn't it, Robert? Triangle in it, though. Yeah, that's what the red triangle. All right. And let's say we have a triangular sign, and it has edges that measure 11 inches. And this, of course, will not be drawn to scale, 14 and 18. Okay. So I just put some kind of triangular sign. Nothing I do today will be drawn to scale. All right. Find the measure of each angle in the sign. I've never been able to do that before. Find the measure of each angle. So you have this all written down. I have to write it out. Okay. So when I look at my two laws up above, I see that my first law, the law of sines, involves knowing at least the sine of one of the angles. And I don't know any of the angles. So when you have a side, side, side situation, does anybody remember side, 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 and angle, side, angle, that kind of stuff from geometry along the way? Yeah, a little bit. All right. So when you have a side, side, side situation, this is like screaming, use law of cosines. So let's take a look at the one law that I've given you. C squared equals A squared plus B squared minus 2AB times the cosine of C. All right. Does that look a little familiar to you? What does it kind of look like? Looks like the quadratic formula. It kind of looks like an identity. Well, it is an identity in some ways, right? What? Pythagorean theorem. If I just take off this last term, does that look like the Pythagorean theorem? Interesting. All right. So I'm just going to arbitrarily do A, B, C. I'm just going to and call this side A, this is side B, and this is side C. I'm just going to label. I'm always going to go A, B, C like that. So I'm trying to solve for the measurement of each of these angles. So I can put C in as 11 squared, A is what? 18 squared, B is 14 squared minus 2AB. A is 18 and B is 14, is that right? Times cosine of C. Is that right? Everybody agree? I'm just plugging in, right? All right. C squared equals A squared plus B squared minus 2 times 8. I got all the numbers in the right place. All right. Now, let's look at something. We notice that if we take that off, it looks just like the Pythagorean theorem. And let's take a look at this last term here. Notice that the coefficient of the cosine of C involves A and B, which are the two sides here. I wonder if that's always going to happen. And that this side here corresponds to the angle there. So you want to try to see if you can see some patterns here. And I'll show you in a minute a little bit more about this. So we got to just throw this into our calculator. So get your calculators out. I'm going to want you to check the work here as I go along. I think we can do this pretty much, well, we'll take it a step at a time here the first time around. So we're going to square 18. We're going to square 14. We're going to subtract. Oh dear. How'd I do that? Thought I hit, I must hit. Let's just do that first. Let's clear this. 18 square. Nope, I hit the same. I can't even see. Where's my glasses? There it is. All right. Now, you can do this a lot faster than I can at this point. Plus, here. 121. What's 18 square? What's 14 square? What is it? 324. What's 14 square? 196. Minus 2 times 18 is 36, and 36 times 14? The sine of 59.7 degrees divided by its corresponding side, 184.5 feet, will be equal to what? Well, let's label these again with our kind of conventional A, B, and C. All right, so now what do I do? Well, I know 125's here, right? That side is across from angle A. So I set up my proportion by saying the sine of angle A is to 125 feet. That ratio is exactly the same as that ratio. It's kind of amazing that all these ratios are the same. I think it's kind of neat. Okay, so we got to solve for sine A, so we multiply both sides by 125. We divide it by 184, and we get the sine of A. All right, so if you check me, I get the sine of A is roughly 0.585. So if I hear 1 or 2 checks on that, I'm going to assume I did it correctly with my count. Okay, 2, 3, woo, okay. So we want to find the measurement of angle A. So I take the inverse or the arcsine of 0.585. And when you do that, you should get approximately 35.8 degrees. Okay, good. So up here, I'm going to write 35.8 degrees. Okay. Bearing in mind that what we want to find is this measurement of theta here. So where can I go from here? What would be next, do you think, in terms of your next step? Yeah, let's find the measurement of angle B right here. So angle B is going to be what? Angle B is going to be 180 degrees minus 35.8 degrees plus 59.7 degrees. Okay. So angle B comes out to be approximately 84.5. So B is approximately 84.5 degrees. So that's right in here, 84.5. So because the original tower was at a 90-degree angle, that tells you that 84.5 degrees plus theta's measurement is going to be equal to 90 degrees. So to get how far the tower has leaned, we subtract 84.5 from 90 and we get theta's 5.5 degrees. And this is accurate. This is not a contrived example. I don't know what's causing it. I used, huh? Oh, they built it on sand. Ooh. I used to know the answer to that years ago because I was curious like Jackson, but I've forgotten what it was. Huh. Trying to think. Where was I just? I was just somewhere and they said, oh, hang on. Great. It was even sunny. Wow. What's the sun? All right. All right. So these next three, the next three problems are important. We're going to work through them, but I want you to try to start getting a sense of when we use the law of sines, when we use the law of cosines, and we're going to run into something called the ambiguous case, right? There's going to be ambiguity, and under what circumstances do we have ambiguity? So let's take a look at the first one. Again, all of these, if you look at all three of these, do they all look kind of similar? If you look, they all have sides of length 10 for A, B is all 15, and in the first two you got C is 75, A is 75, and B, and then you got 25 in the final angle. So you got three situations here where two of the sides are all the same in every picture. So let's take a look at the first one. A equals 10, B, these are going to be the problems you're going to like to have on your test because they're pretty straightforward. So, you know, again, I'm not drawing anything to scale here. I'm just going to do ABC. And A is the side opposite my angle A. B is the side opposite my angle B. And C is, oh, do I know C? No, I don't know C. That's unknown. But what do I know here? I know measurement of angle C is 75 degrees. And you can tell from this picture that that definitely does not look like 75 degrees, but it's okay. Okay. All right, so look at the directions. It says solving a triangle means finding the measurement of all three angles and the measurement of all three sides. So we've got our work cut out for us here. All right, we've got to find all three angles and the measurement. Well, we've got two of the sides. We only need one. Let's find that other side right now. Let's find C. Why not? Right? We know, oh, we can't, can we? Can't do it. Why not? Because we've got 75, sine of 75 is to C, but we need another angle to use our law of sines. So we must start off with our law of cosines. So we're trying to find C. So C squared equals A squared plus B squared minus 2, and then it's always going to be AB times the cosine of the angle that's whose side is right there, big capital C. So let's see here. We've got C squared equals 10 squared plus 15 squared minus 2 times 10 times 15 times cosine of C. C squared equals 100 plus 125 minus 20 times that is what, 300 times cosine of C. And what was C, by the way? 75. So otherwise you wouldn't be able to solve this. So you just throw in your little 75 degrees right here. And then you're just solving for C squared. You've got all the information you need. So 225 minus 300 times the cosine of 75 degrees. And hopefully when you do put all that into your calculator, you get C squared's approximately 247.354. So C, when you take the square root, it's about 15.7. That's just calculator stuff, all right? So 15.7. Okay, 15.7. Do I have any checks on that? Yeah. Ooh, all right. 2 checks. All right. So that's just. Oh, okay. All right. So what you get? You should still get 15.7, even though I didn't put in the right number there. Okay. I've got it all worked out, so I was just. All right. Now, woohoo, we only need to find 2 angles. Now, law of sines enters the room because that's the easiest one to use. So let's see, I got a 75-degree angle here. I always like the angles that aren't rounded. So the sine of 75 degrees to its corresponding side, which we just found 15.7, is going to be the same as the sine of angle A to its corresponding side, 10. I multiply both sides by 10. 10 times the sine of 75 degrees over 15.7 is going to equal the sine of capital A. So that comes out to be about 0.614 when you do all that calculator work on the left side here. That's 0.614 approximately. So now I've got to find the angle whose sine is 0.614. That's the arc sine of the cosine inverse. So sine inverse of 0.614 or the arc sine of 0.614. Remember, arc sine and sine with the -1, those are inverse of sine. They all mean the same thing, both of those notations. And if you do that work out, you get approximately 37.89 degrees. Let's see, what do I have now? I've got 37, I'm just going to call it 37.9 degrees. So I'm essentially done now because I have all 3 sides. Let's highlight them. I have all 3 sides. I know C, I know B, and I know little a. And what are my angles? I know angle C, I know angle A, and now all I need to do is subtract the sum of these two, 75 degrees plus 37.9 degrees from 180, and that will give me big capital B, which is 67.1 approximately, 0.1 degrees. Don't forget your degree symbol all the way through, otherwise it's known as radians. So we've got all 3 angles and we've got all 3 sides. Cool. Done that. Any questions on that? Let's take a look at the next one. It looks almost the same. I don't have my paper here, do I? Yes. We got 10 and 15 again, but now angle A is 75 degrees. Well, angle A is 75. Oh, angle C was 75 here. So let's take a look at this one. All right. Little warning, there's a surprise coming up. So again, I'm just going to do I'm not doing anything to scale. Nothing looks like it's supposed to. Okay, this is 10. This is little baby A, and B is 15. C, we don't know, but angle A now is 75 degrees. All right. So the first thing I see when I look at this is I see a pair. I see an angle with its corresponding side. I see an angle side pair. I'm really excited because I can use the simple law of sines. So sine of 75 degrees divided by 10. Okay, so let's see. Which one do I want to solve for? Well, the only other one I can use, the only other ratio, has to involve capital B because I know little b. So I'm going to say sine of capital B over its corresponding side, which I know 15. All right, simple proportion to solve. 15 times sine of 75 degrees over 10 equals sine of B. Okay, so let's put this into the calculator. Sine of B. All right. If you have a calculator, want to check me, I'd appreciate it. So I'm going to clear everything out, try to take my time here. 15 times sine of 75 degrees, the whole thing divided by 10. Okay, sine of B is 1.45. Okay. Is that okay? No? Sine of B. So let's, nobody said anything, but before Hazel just said that, let's try to find the angle whose sine is 1.45. So we take the inverse of 1.45 to get our measurement for B, and look what happens. All right, I'm going to put this in A. I'm going to store it so I can get the full-blown answer here. There we go. All right, so inverse sine of alpha A is, what? I must have put something in wrong. I didn't make, let's see. I'm going to try it again. I don't know what's going on here. Inverse sine, whoops. Inverse sine of alpha A. Come on, baby, give me something in degree. Ah! But look what it says up here. Error domain. It's like staring at you in the face. You've got a domain error. What's the range of sine B? The function sine of theta. Y equals sine of theta. What's your range? -1 to 1. Can we get 1.45 out of that? No. Okay. So this particular triangle, first of all, this angle B, there's no angle B that exists that can have these measurements. No angle exists, therefore no triangle exists. No triangle exists with this given information. Impossible to build a triangle. So A gave us a triangle, B gives us no triangles. What do you think might be left as a possibility? Have a triangle. Think about your quadratic equation. You can have no real roots, one real root, or two, right? So maybe we can get two triangles with some measurement. So let's take a look. That's why this is called ambiguous. Because what are we given in all three of these? We're given two sides and an angle, aren't we? All three of these, A, B, and C, we're given side-side angle. The angle's not included. In other words, if you had a side here like, I'm just making this up, 12, and a side here like 14, and you knew that angle, that's called an included angle. That's written this way, side angle side. It's the sassy case. That's a way of proving congruent triangles, just like side, 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 and angle, angle, angle. You can't prove congruent triangles with this. So when you know two sides and some other angle, you have a situation where you could have two different triangles, one unique triangle, and absolutely no triangles. So let's take a look at C. So you start off, you know, you're playing your music and you think, I'm just plugging stuff in here. You're not paying too much of attention. So you just kind of go along. Life is good. 10, 15 in C, and you know angle A is 25. You say, okay, here we go. Law of sines. So the sine of 25 degrees divided by 10. Okay, what other side do I know? I got side A. Oops, I know side B. I've already used my angle. Side B is 15. So up here I can put sine of B. This is how we started the last one off. So hopefully we'll have a little bit of luck. 15 times sine of 25 degrees over 10 equals sine of B. Let me just tell you, we are lucky in this case. The sine of B is it 25 there? Yep. C is on the other side. So I don't have B, sine of B, but the angle B is about 39.34 degrees. Okay, so I put in my 39.4 degrees here, or 3 degrees. I'll put 3,4 in. What the heck? 3,4. All right. And now I haven't finished my story because I can find angle C. Angle C is 180 minus 25 degrees minus 39.34. So angle C is roughly 115.66. Okay, and clearly that's not an obtuse angle there. All right, so again, it's not to scale. All right, so all we have left to do here is find side C. Oh, okay, I'll use my law of sines again. Why not use sine of 25 all over again? That's probably in your calculator somewhere. Save you some time. Divided by 10 equals 115.66. Sine of 115.66 degrees all over C. And you do all that workout, and you get C is approximately 21.33. And you're happy. You turn to the next page, and you think you're done. All right. Let's come back here. We're not done. What? Let's come back here. Let's work that out. I didn't give you all the answers for that. So someone want to put this in their calculator for me and tell me what you get? 15.634. Okay. So we know if we're on our unit circle, and we go up as high, this is our output value, about 0.634. We know the top is 1, so a little more than halfway. Here we go. So the sine of that angle B is 0.634. We also know there's going to be another angle that goes from the initial side to that terminal side that also has B, which is what? 39.34 degrees as its reference angle. So there's going to be another angle for B other than 39.34. So we've got to find it. So you have to say, okay, this is one situation for B. What's the other situation? Hang on, we got to get the radian value first. If this is 0.634 over here, pi minus 0.634, and what's that going to be? 2.508. So now we've got to find the sine inverse of 2.508, and that's going to give us a totally different angle for B. So if you take the sine inverse at 2.508, you should come up with, if I can find it here, 144.66 or 140. I can't read my writing. I think it's 144.66 degrees. So this is definitely an obtuse angle. So B, if this is B, is now 144.66. So now you have to find your other angles based on that and your other side. Okay. So now you have two triangles. So when you're given information for side angle, you have 3 different situations: 2 triangles, 1 triangle, or no triangle. And when we start class on Wednesday, I'll show you, if you haven't seen that optional video, I'll show you the little geometry sketch pad. But I'd like you to just take some time now. I've just given you a few problems to work on for your lesson activities, not a lot, just 3 typical type problems you might have. I didn't draw the triangles, I gave you the information. And then 1 situation where you have an application. I would say work through one of these just to get used to using the properties, and then start working on this, because you'll see something like this for homework. So if you have any questions, we can go over it now. Okay, so that's it for our test for Friday. That's the last